Hello students, this is the third lecture regarding calculus of variations. In fact, this is third lecture. It is written one over here. This is third lecture 3 on calculus of variations and mechanics. So in this lecture, we are going to discuss certain numerical examples based on the discussion carried in last two lectures. So in numerical problem, first we consider the main problem or the fundamental problem of determining the shortest distance, the path of shortest distance between 2 points. Here you are given that there are 2 points. You are given there are 2 points in a plane, that is A is here. I have already mentioned this earlier. I have given you the description of this type of problem, but here we have to find the solution of this problem, that A and B can be connected using these two paths, can be connected by this path, but you have to find a path of shortest distance. So obviously even for a layman, as I told you, that you can see that the shortest distance from A to B can be traversed by a straight line, through the straight line path. But how we obtain this in view of the calculus of variations, that is the main agenda of this lecture. You see, I have also explained in the last lecture the arc length of any curve. Suppose you have this curve here, and then the arc length, the small arc, is given by this formula. I have already explained in the last lecture. Yes, sir. And when you are finding the arc length between the 2 points A1 and A2, and corresponding to those points the y coordinate is, this is B1 and this is B2. So that is how the boundary conditions are formed in this situation. So this is the functional now, and now you have to find the extremal of this function. Definitely you are going to use the Euler's equation that gives you the necessary condition for the existence of extremum, right? So now in this case we have f equal to this one, and you can see in this f y is not appearing explicitly. Y is not appearing, however x is also not appearing explicitly, but you look at this in view that y is not appearing explicitly, or you can say this f does not depend on y. Therefore the Euler equation reduces to the case 1, and in case 1 you already know we had Euler equation reduces to in this form. Euler equation in that case reduces to this form. Means you have to differentiate that f with respect to y dash partially, and corresponding to this you get this expression and equal to c. Now when you solve this, what do you get? You get y dash square equal to c square 1 plus y dash square. When you simplify it, you get y dash square 1 minus c square equal to c square. That implies you can have y dash square equal to c square divided by 1 minus c square, and that implies y dash equal to under root c square 1 minus c square plus minus whatever it is. You can consider all that as a constant. All the things there are appearing constant, That implies you can write y dash equal to the some constant t. So that is how this thing is coming over here. So you can say from this solution you get y dash equal to c when where d is any constant. If you integrate this, y dash stands for basically y dash stands for dy by dx equal to d. When you integrate it on both sides, you get y equal to dx plus e. E is the arbitrary constant. Now, solving that Euler equation, you have obtained value of y. Value of y is dx plus e, and this is the equation of a straight line. So what does it mean? It means that the distance between 2 points A and B is minimum when we move from A to B through a straight line. So this is the mathematical explanation of that fact. So this gives you the proof of this problem. Now the next problem, this can be any extremal. You have to minimize this functional. Find the extremals of this functional where conditions are given y at 1 is 0 and y at 2 is 1. These boundary conditions given to find the arbitrary constant appearing in the solution. For example, here arbitrary constants were d and e, and d and e can be obtained, could have been obtained using the conditions that y at a1 is b1, y at a2 is b2. So in the same manner, wherever boundary conditions are given like this, then you can obtain the value of the arbitrary constants. So now again, in this case, f is this one, f is this. So again you can say the y is not appearing explicitly, and you can use the same type of the Euler equation. That is case 1, f y dash equal to c. F y dash means you take the partial derivative of this part with respect to y dash and you get this type of expression. Further, when you simplify this, you get this type of expression, and you, as I mentioned, y dash means dy by dx, and you integrate on both sides, you get integration of this plus c1. Right. So now, when you get the integration of this, you get this type of expression. How it is that you are having multiply or divided by 2 here, and this you take 1 minus c square x square power minus 1 by 2, you take it on numerator or into 2x by 2. So it gives you the basically the form. It gives you the form into right here. This is in the form fx f dash x dx and fx power n, suppose dx, then the integration is given by fx raised to power n plus 1 divided by n plus 1. So you can utilize this formula for the evaluation of this integral, and you will get this thing. So in this case, this fx will be, fx means 1 minus c square x square, and n means minus 1 by 2, and here you will write 2x because you multiply it with 2 and also divide it by 2. You can write here 2. So in this way, when you apply this formula, then you will get this type of the result. And again, on simplification, you take y c1 on left hand side, y minus c1, and rest of the things on this side. So finally, you will get this type of the equation. And what is it? This is the equation of a circle whose center is at this, and this is a point on y-axis, and a radius can be calculated by the formula as given in the geometry. Right. So using the boundary conditions, we can find the value of this arbitrary constant, and it comes out to this. This is the final solution. Now moving further, next example, find the curve passing through x0, y0, x1, which generates the surface of minimal area when rotated about the x-axis. So what is the situation here? This is problem of finding a minimal, not the maximal curve. Means suppose this is x-axis, origin, y-axis, and there is some curve at which the 2 points are lying. The point A having coordinate x0, y0, and point B having coordinate x1, y1. So you have to find from these 2 points many curves may pass through. Many curves may pass through. Suppose this is another curve that can pass through, this is another curve that can, and many more curves. And when we revolve these curves about x-axis, then which one is the curve which generates the minimal surface area? That is our problem. To deal this problem, we see here x0, y0 and x1, y1, these are given points on the same side of x-axis as I have shown in the figure, and let y equal to yx be any continuous curve joining these 2 points. And you can say the boundary conditions can be expressed like this, because the coordinate is x0, y0, means value of y at x0 is y0. Similarly, value of y at x1 is y1. When we rotate these about x-axis, you should remember this formula. You should this one. You remember this formula to for the area of revolution. You see, this is the formula for area of revolution. So you have any curve y equal to yx, and if you revolve that curve about x-axis, so in 3D manner, then the area generated will be given by this formula. So in this case, if the 2 pi is constant, you can consider that f is this thing. So now in this case, x is not appearing explicitly, x is not appearing. So in that case, we apply this case. The Euler equation is now this one, discussed in the cases. So you put value of f here, y dash, and fy dash will be this quantity. On further simplification, we get where y dash is this, and separating the variables, you find the value of integration, and it comes out to be finally this in this form. And this is the equation of catenary. Catenary is the name of a curve. Generally, a catenary can be represented in this manner here. Catenary is like this. This type of curve is the catenary. So it gives you the solution of this type problem, which generates the minimal surface about the x-axis. Another numerical. Now, based on the way explained here, you can solve certain exercises. This is the Brachistochrone problem. I also explained this problem in the last lecture here, lecture number 2. That this is something, a problem of determining the path along which a particle takes minimum time to reach a point B under the influence of gravity. Under the influence of gravity. So this is the problem. So basically, you have to minimize the time. So you have to first obtain here functional form for time. Functional form for time. First thing you have to obtain over here. And these are direct questions. Here it will be f. Here this is capital F, capital F, capital F, and you can apply the Euler theorem according to the cases. And you can sometimes, it also gives you the proof if you directly apply the fundamental Euler's equation. Another problem to solve: find the continuously differentiable function yx which minimize the integral this and satisfies these conditions. Similarly, this is a problem as was discussed in case 4. K is 4, here it is capital F. So you solve these questions. If any problems you find, then we can discuss in the live interaction session.